Our project aims to solve the problem of the outstanding reliance our society has on fossil fuels by utilizing the world's oldest form of solar energy, biomass. Whether you look at universities, small businesses, or homes, biodegradable products are always readily available and often wasted. Biomass gasifiers break down the chemical components of biodegradables and convert them into a biohydrogen that can be synergistically used in engines. Backyard gasifiers have long been used to create biogas, but oftentimes are very inefficient, dirty, labor-intensive, and unsafe. Our goal is to design and build an automated biogas reactor modeled after those that have come before. The goal of this is to create a user-friendly, self-reliant energy conversion system so that just about anyone can operate the device effortlessly and as safe as possible. The system will need to automate the following: initiate combustion, combust wood fuel in combustion chamber, pull gas from combustion chamber via suction, clean gas via filtration system, and recycle produced gas for later use as ignition fuel. Valves will be controlled by a microcontroller via temperature, pressure, and flow data. Gas leaving the reactor must be cleaned via filtration system. Output should meet Clean Air Act standards. Once combustible gas is produced, a small holding tank must be filled to a predetermined pressure so that the system can self-start during the next production cycle. Automation is key to our system's uniqueness. It allows the system to monitor itself and make adjustments based on data gathered through the microcontroller. Typical gasifiers of this scale must be constantly monitored, and are unsafe due to limited ability to shut off the system if something got out of control. Our system is designed to seamlessly adapt through several operating conditions depending on multiple temperature and pressure sensors found within the system. The first stage is when the reactor is starting. The blower is on and valves 3 and 2 are closed, while valves 1 and 4 are open, allowing starting gas to be injected into the combustion chamber as the sparking sequence is executed at the combustion chamber ignition point, and exhaust gases are sent out through the flare stack. Valve 4 closes after a few seconds, and the remainder of the system is maintained until the reactor has reached steady-state pyrolysis temperature and the exhaust gases are combustible, which is determined by executing a second sparking sequence at the flare stack, causing ignition when in the presence of combustible gas. A thermocouple at the flare stack will detect this change in temperature, causing the microcontroller to configure the system for the operating stage. The operating stage initially consists of having valves 1, 3, and 4 closed and valve 2 open, until a pressure sensor at the gas holding tank indicates to the microcontroller that the tank has been recharged, at which point valve 2 closes and valve 3 opens, providing fuel to operate a generator or other power-consuming device. The final stage of the system is the shutdown stage. Valve 1 is open and valves 2, 3, and 4 are closed, while the blower continues to pump the exhaust through the flare stack for several minutes as the reactor cools. This concludes the operating conditions of the control system. To build our prototype, we fabricated a downdraft biomass reactor with ash shaker, a copper coil heat exchanger, and a multi-stage filter. Our biomass reactor is made from a 4-foot propane tank, which we cut open at 2 points. Within the tank, we have a combustion chamber and pyrolysis zone, which are made from 1/4-inch steel that has been machined to our specifications and welded together. The reactor also includes an ash grate and shaker system. The reactor comes together with 1/4-inch steel flanges, which we had plasma cut from a vendor in Bakersfield, California. Our copper coil heat exchanger is comprised of 2 parallel 1/2-inch copper tubing lines that have been rolled into concentric coils and are submerged in a stainless steel tank, allowing heat to transfer from the hot gas to the cooling fluid. There is a drain at the heat exchanger outlet to allow for any condensate to be collected and be removed from the system. Our filter is made from a 1-foot propane tank with pipe fittings welded at the top and bottom for the inlet and outlet, and a door in the side of the tank that allows for servicing of the filter mediums. We also made our own PCBs, or printed circuit boards, etched with ferric chloride. Due to the large scope of our project, Testing of the control system with the physical modular systems had to wait until manufacturing was completed of all physical systems. During testing, we worked out bugs in our control system code, as well as ensuring proper seals at the various subsystems. Testing uncovered that our pump was not strong enough to recharge our starting gas holding tank, and that if we were to make a second prototype, we would need to incorporate a compressor to achieve the pressures we desire. Unfortunately, during what turned out to be our last test, we experienced a catastrophic failure of our pump, preventing further data to be collected on the performance of our project. We would like to thank Scott Huffman of HMF Industries, Jim Gonzalez of Garzel's Machine Shop, Jonathan Song of San Francisco State University, and Thomas Putney